Hey kids, long time no see. That's a joke because I just recorded my last video, so it was really funny. But this is a really important lesson for our next unit, and that's where you're going to have your next project. So pay attention now as you start this problem. Clearly the answer is B and C because they're the same height. So first we're watching a video. Cool video. All the steam exits the branch because wood and most living things have a lot of water inside them. And then when the water's all gone, the whole thing bursts into fire like instantly. We'll watch again. Some steam escaping. You can hear it. That's like a tea kettle sound. The steam escaping. Okay. We gotta go back to the do now first. The do now is basically the loop-to-loop. Let's say I have a certain height and a certain height. Let's say, oh, keep it simple, 10 meters. And let's say a ball is going to roll down the hill. As we saw in the video, it could take a loop-de-loop path. Let's say it could also take this path. There's a second hill, super steep, basically a straight free fall down. And let's say there's a third hill. We saw in the do now that the ball will have the same speed at these 2 points. That's because it has fallen the same height at those 2 points. So the same amount of u has turned into k. mgh has turned into 1/2 mv squared. So a very similar question, not a trick question. You should be able to do this. If the ball goes down the steep hill, the medium loop hill, or the very gradual shallow hill, after which hill will it have the highest speed? Assuming no friction, no rolling, no loss of energy, which hill will give the ball the greatest final speed? Yes, good job, excellent. It's all the same final speed. The mass cancels, and the final speed will be square root 2gh. No matter which path you take, this is a really important idea. The path doesn't matter. If the starting height and ending height are the same, the final speed is the same, regardless of which path, which of the 3 paths. It seems really weird. In real life, friction will affect it a lot. But in theory, in physics theory, if there's no friction, they'd all reach the same speed. Okay. This is an important idea. U is mgh. Well, ug equals mgh. So, let's say g is about 10. If I put 5 kilograms of mass up here, then u would be 5 kilograms times 10 meters times g, which is also 10, 500 joules. So 5 kilograms, 500 joules. If I put 10 kilograms, it would be 1,000 joules. If I put like 420 kilograms, it would be 42000 joules. For this hill, this hypothetical hill, the mass I put there is always multiplied by 100 to find the energy held by that mass. The energy per mass is always the same ratio. For this hill, it's 100 joules per kilogram. It's GH, energy per mass. Got it? Okay. So, the energy per mass at the top of the hill is 100 joules per kilogram. What's the energy per mass at the bottom of the hill? 0. Good job, buddy. 0. 0 joules per kilogram. This is going to sound really obvious. You guys know how ramps work. If there's no friction, or there is friction and the object's allowed to roll, objects will always naturally roll or move or slide or whatever from high heights to low heights, or high energy per mass to low energy per mass. If I had a ramp, here I have okay, don't tell any preschool teachers that I'm borrowing their stuff, but if I have a nice ramp that I tilt like this, a marker will always roll from the high height to the low height. If I put it on the low side, it'll never roll up to the high height. That doesn't make any sense. It'll always go from low to high. And the speed it goes from low to high, let me say this carefully. The speed the object rolls from low to high is based on how much higher the high is than the low. If they're almost the same, if the high side is like a centimeter taller than the low side, it'll be like, oh yeah, I guess I'll kind of roll slowly across the laptop. But if the high side is really high and the low side is really low, aka it's a very steep slope, then it's going to roll super fast from high to low. So obviously, if you were a normal person, you would say, oh yeah, objects fall from high to low heights. But for some reason, physicists say this. They say objects naturally move from high potential to low potential. This GH, it tells you an object's gravitational potential energy. An object will naturally move from the high potential to the low potential. 100 joules per kilogram is a lot of potential. Every kilogram of mass will have 100 joules of energy. But over here, it'll have 0. So objects will naturally roll from high potential to low potential, not vice versa. Gravity makes them do that, which seems obvious. So let's move on. Okay. Energy per mass is GH. Last week, we talked about force per mass and force per charge. To be specific, it was gravitational force and electrostatic force, or electric. Gravitational force per mass is Fg over m. Electrostatic force per charge is Fe over q. This was g. Not acceleration due to gravity, gravitational field strength. This was big E, electric field. So now we're going to do the last piece of the puzzle. Not energy per mass, energy per charge. We've only learned 3 kinds of energy so far: kinetic, gravitational potential, and elastic potential. But you know, if you've used electronics before, which you're probably doing right now, that electricity also must have energy in some way. So there's another kind of energy, electrical potential energy. We're not going to learn the formula. We're just going to appreciate that it exists. Keeping that simple. It exists. It must exist. Of course it exists. It definitely exists. Energy per charge has a very, very common name. It's used a lot in physics. It's called voltage. Capital V is a symbol for voltage. And the units of voltage are volts, which is really annoying, but that's the way it is. So, let's say UE is my electrical energy, and I divide by the charge. So let's say I have let's say I store 12 joules of energy in 4 coulombs of charge. That's my voltage, 3 volts. If I have 12 joules of energy in 4, let me write it out. 12 coulomb, nope, I keep saying, teaching physics is too hard. I gotta retire. 12 joules of energy in 4 coulombs of charge. That's 3 joules per coulomb. Another word for coulomb, for joules per coulomb, is a volt. And this gets me really annoyed. Like when people say, "Oh, what's the kilograms of this ball? Is 5 kilograms?" No, it's not right. The mass is 5 kilograms. So don't say, "Oh, what's the volts? It's 3 volts." But you were almost right. The voltage is 3 joules per coulombs, or 3 volts. So volts and voltage have the same symbol, V. A volt is a joule per coulomb. It's the energy held by some charge divided by that charge. Yeah, energy held by the charge divided by the charge. We'll come back to this. Okay, time to get back to basics. Imagine there is no electricity. There's no electrical energy. We just live in like the Stone Age. No, the Dark Ages. Medieval times. As we said earlier, objects will naturally move from high to low potential. Yeah, you could say high to low height, but high to low potential makes it sound more physicsy. So here's a beautiful mountain with a beautiful river. Rivers flow from like the mountain's ice cap, and they flow down into the ocean. Rivers always flow downhill, never uphill. Ancient people in medieval times knew this because they were super smart, just like you. And they always would build their house right next to the river. So they could A, drink the water, B, like wash their clothes and stuff, C, transportation. But one important use of building your house next to the river, you can build a water wheel in the river and use it to like grind your grain or something. This analogy makes sense, don't worry. The water is flowing from high to low energy. The water is losing energy. You can make use of that and make the water do work for you. So people in like the pre-industrial age, they said, this water is flowing. It has a lot of energy. I'll use that energy so that I don't have to grind my grain by hand. I'll put it through a water mill, and that'll grind my grain and make me bread automatically. Like in Minecraft, you have to like take the wheat and like put it in the crafting bench and turn it into bread. Is that true? Whatever. Yeah, you have to grind up wheat. You can't just eat grain. You have to grind it first. So people used to build water mills, and yeah, the energy lost by the water is gained by the mill and used to grind wheat. All right. Let's say there's a whole village of people and they're not that smart. They don't say, I'll be a miller and you be a farmer and you be a blacksmith, they all say, I like to eat bread, so I want a mill too. So every single house says, man, I want my own river. Could they split the river, just divert the river so the river goes into everyone's house? If you were one of these like medieval villagers, would you want a river going into your house? What's the problem if you dig a dig a canal and the river flows straight into your house? What's going to happen after a certain amount of time? Why is this not really ideal? How come this house has a good setup, but these houses are going to have some problems? Tell me now. Okay, this is a silly example, silly analogy, but it's going to work out. I believe myself. Yeah, the water will flow into the houses. It's going to flood the houses. So you're going to have too much water. They're going to be underwater and very sad. In order to use the energy from the water properly, you need the water to flow in and flow out. You need high energy water coming in, but you also need the same amount of water leaving. If 100 gallons of water flow into your house and 99 gallons flow out, you actually are slowly flooding your house. That's very bad. You want the same amount of water coming in as coming out. You're not taking the water, you're taking the water's energy, but the water still leaves. This is a really important analogy. Not for actual millers, but that's the idea. Way back in the Dark Ages, if you wanted to grind grain, you have to have a river. You'd have to have the river flow in to your house and then flow out, or flow into your property and then flow out, because otherwise you're gonna have a flood, and that's not gonna work. If your whole mill's underwater, your bread's gonna be gross. Whatever. This kind of strange, but nowadays every house that everyone lives in has their own river. Except it's not a water river, it's an electricity river. These little surprised faces in the wall of your house, they have a very specific use. On one side, you have high energy charge flowing in. The other side, low energy charge flows out. It has to be the same amount of charge. What would happen if it were not? What would happen if charge only flew into your house and never flowed out? Yeah, that's right. It would be bad. It would be bad. So for a water mill, a water mill, high energy water flows in, low energy water flows out. For your house, high energy electrical charge flows in, low energy electrical charge flows out. And if you want to be very fancy, it's actually electrons, which are negative, going the other way, but it's the same idea. Charge flows in one way, the same amount of charge flows out the other way. The difference is it flows in with more energy and out with less energy. The prong in the middle, the third prong, someone asked this in class, that's to balance out if it's not balanced. We don't want our house to be flooded with water or electricity, so this will ground our house if there's too much charge of some kind. If you live in an old house and you don't have that third one, be careful, watch out. So that's the idea. Okay. Let's say you need 100 joules of energy. Let's say you need 100 joules of energy to grind some grain. So you install your water mill and dump in the grain, and I don't know, like 100 joules. You need you need 100 joules of energy. Let's say you let 25 cubic meters of water, no, 25 kilograms of water to flow through, but that only gives you 50 joules of energy. So, let's say 25 kilograms of water goes through your water mill, but that only provides you with 50 joules of energy. How much water needs to flow through your mill in order to give you 100 joules of energy? Hopefully that question made sense. If it did, it was pretty simple. If 25 kilograms of water gave you 50 joules of energy, then you need 50 kilograms of water to get 100 joules of energy. You have to double that. The energy per mass is 50 joules over 25 kilograms, which is 2 joules per kilogram of water. That's the energy per mass. Voltage, we said, is the energy per... Oh, I'm not going to use E, that's electric field. It's the energy. Remember, work is change energy, so work is fine here too. Work per charge. So, instead of a water mill to grind my grain to make my bread, I'm using an electric grain grinder. And my electric grain grinder needs 100 joules of energy to grind 1 loaf of bread's worth of flour. Pretend it works. Yeah. If I know how much energy I need, and I know that every 1 coulomb of charge gives me 5 joules of energy, then I would need 20 coulombs of energy. No, 20 coulombs of charge flowing in this terminal and out this terminal to give me 100 joules of energy. I made a very, very important mistake that you should not make. Do as I say, not as I do. Don't use energy and electricity, charge, the same. Charge is in coulombs. Energy is in joules. Charge is like the water. The water has energy. It isn't energy. The water flows in with energy. It flows out with less energy. The charge flows into your house with high energy. It flows out with low energy. It gave your house energy, and you use it to power your wheat grinder, or run your gaming PC, or turn on your lights, or charge your laptop to study physics. But the charge came into your house with energy, and it left without the energy. The energy per coulomb of charge is known as the voltage. This is not right. This is fine. This is right. If I ever say that I'm not right, I'm joking. But in the US, the household voltage is not 5 volts, it's 120 volts. I'm just checking nothing right now. Hopefully everyone's having a great day. Hopefully everyone's learning a lot of physics right now. Last lesson of the unit. Yeah, 120 volts, exactly what I was talking about, 120 volts. So, if 1 coulomb of charge comes out this hole through your wheat grinder and out the other hole, you gained 120 joules of energy. If 2 coulombs flow through, you gain 240 joules of energy. If 3 coulombs flow through, you gain 360 joules of energy. This is the ratio of energy per coulomb per charge. It's the number of joules of energy you get for every coulomb of charge that flows through your house. That's voltage. What else do I want to say? Voltage is a scalar, not a vector. So very conveniently, we can ignore direction for this whole unit. And yeah, that's it. charge will naturally flow from high to low voltage, just like masses naturally move from high to low height or high to low energy. That's voltage, capital V. It's also called potential difference for some reason. So if you see the word potential difference, that's also voltage. And this will be really important next unit. So watch this video if you didn't, which you just did. Okay, bye.